Thank you. So I'm going to talk about MAIHDA, which is a new method for studying intersectionality. So as an outline to this talk, I'll start by saying what I mean by intersectionality, and then I'll go in to demonstrate this method, models and some results. But I want to get to the point where I can go beyond that and actually discuss the methodological work I've been doing about the statistical properties of different types of predictions from these models. So that's where I want to get to. So first of all, what is intersectionality? It's the study of how various social identities intersect with one another to affect individual outcomes. Okay, so these social identities might be gender, ethnicity, socioeconomic status, and so on. And there's a great keenness to make visible what might be unknown kind of outcomes and experiences of particular combinations of characteristics, which aren't necessarily what we think from the state of knowledge we have currently. And ultimately, this is trying to push for a more equitable and just society, really, by better knowing the extent of inequalities. So, the traditional approach to studying this is to do regression with interaction terms. So if you are interested in student reading achievement and you're interested in gender differences and student immigration status differences, you would do a regression of reading scores not just on gender and immigration, but gender, immigration and interaction. And the interaction would allow you to see whether the experience of that particular subgroup, let's say female immigrants, was unusual in the sense that it departed from additivity. Now, the whole point of intersectionality is to consider multiple social identities, more than just two. But the problem is you have 3, 4, 5 identities, and if you consider all the interactions, which is what the intersectionality theory would encourage, the regression models get overwhelmingly complex. Now that leads a lot of analyses to go simpler, to only consider a subset of interactions, maybe just 1 or 2 two-way interactions. And then they run the risk of missing important complexity going on and mischaracterizing the outcomes of all the intersections which are out there. So this brings us into MAIHDA, which is a new approach proposed in 2018 in social epidemiology, but is now starting to take hold in education. And essentially, it is an application of classic two-level multi-level modeling. We have students at level 1 nested within intersections at level 2, where those intersections are defined by the social identities of interest. And so we want to know about intersection mean differences. This contrasts standard multi-level modeling, where you might have students within schools and focuses on school mean differences. There are 4 things which we like to find out in an MAIHDA analysis. The first is, what is the general importance of intersection inequalities? How important are they in general? The second is, can we reliably predict what the mean outcome is in each and every intersection? The third is, to what extent are those mean differences really just kind of what we'd expect from additive main effects, or to what extent is there this non-additive component going on? How important are these non-additive terms? And fourth, in terms of each and every individual specific intersection mean, can we break that down into that part which is what we'd expect from an additive main effects world, and that part which is extra. So let's have a brief illustration taken from a paper by Leonard Keller. She analyzes student PISA reading achievement scores in Germany 2018 and focuses on 4 social identities: student gender, student immigrant status, and then the student's parental education status and parental occupation status. Collectively, those 4 social identities results in 40 intersections when you consider all possible combinations. So in an MAIHDA analysis, you fit 2 models, and this is what they do in this paper, of course, as well. And so the first one is an empty 2-level model. So YIJ would be the reading score for student I at intersection J. And this is modeled in terms of the true intersection mean, beta 0j, a quantity of interest. The first thing which is done is we quantify the extent of the inequalities. And so the VPC statistic or the ICC statistic and classic multi-level models will do this. What is the degree of clustering attributable to the clusters? What is the degree of variation attributable to the intersections? The second thing we get from MAIHDA is a predicted intersection mean, because the beta 0j is the true one of interest, but we can predict it from the data. It's better than an observed intersection mean because we have this empirical Bayes prediction which shrinks that observed intersection mean towards the overall average, and that has desirable statistical properties, which I'll come back to in the methodological focus of the talk at the end. But in terms of the study, the VPC is 0.16, and so we would say that 16% of the variation in reading achievement is between those 40 intersections. 84% is beyond that. And so that can be compared across studies. And here are the predicted intersection means, 40 of them for the 40 intersections. The vertical variability, the range of it is some 150 points, which is big, pretty meaningful. There's 1.5 standard deviations in PISA. But also we see some suggestion at interactions. So if you look at the red versus the blue, girls versus boys, that gender difference varies in magnitude as a function of the other social identities across the top. And that is suggestive of interactions. Now, the way we get at that with the MAIHDA analysis is via the second model, where we now enter the 4 social identities as additive main effects. Okay, so we're really characterizing the true intersection mean for each and every intersection as equal to that part is what we'd expect from an additive main effects world, and a kind of naive approach. But then we're adding on the discrepancy, which is effectively what is unique, or the interaction term. And we're interested in the relative importance of these two things, and that's characterized by this PZV statistic, which is the relative importance of the additive part, and 1 minus that is the relative importance of the interactions. And then once again, we can predict the intersection means with the observed intersection means now shrunk towards not the overall average, but the value implied for an intersection by the additive main effects. And that also allows us for each and every intersection to decompose what's going on. And so what you find in the German study, it actually turns out that 91% of the variation between intersection means can be characterized by additive main effects, just 9% due to interactions. So that's a very nice statistic. Here are the interactions being plotted, and whilst their magnitude can go beyond 10 points, so more than 0.1 of a standard deviation in 6 out of the 40 cases, actually in only one of those is it statistically significant. And so we're struggling on an intersection by intersection basis to identify, to separately identify the interactions. Okay, we're now ready to shift into, I've done my kind of review at high speed of intersectionality. We are now ready to shift into these intersection means. Going back to the German paper, they present a table where you got the predicted means from model 1 and the predicted means from model 2. And if you go down those numbers, sometimes they're very similar, sometimes they're divergent, and sometimes they diverge a lot. So intersection 37, we've got a 30-point difference in the predicted mean across the two models, which is 0.3 of a standard deviation. So which model is better? Now those differences are much larger when we have a very few students per intersection, which is quite common in these analyses. So we really want to know which model we should be picking. Okay, so really we're saying what is the difference between this prediction in model 1 and this prediction in model 2? Well, intuitively model 2 is going to be better. It's a richer model. It's got these additive main effects in that prediction, so that must be better, surely. Well, can we do better than just saying that? Well, we can, because we could turn to look at some analytic results. So the first thing I've looked at is at the distribution of intersections. So if you like, imagine a world where the VPC is 0.15, similar to that study, the PCV is 0.9, similar to that study. We've got balanced stratums that are all the same size. Now that's very different, but that's not crucial for this result, but it's simpler for doing the analytics. This is the variance in the stratum means by different methods, the coloured lines. So if we consider a world where the true stratum variance is the black line, 0.15, relative to that, the variance when we look at the observed stratum means in any given sample will be bigger than that because there's a noise component. So that vertical dashed line is when the intersections are of size 10. So you've only got 10 kids per intersection, the variance in the observed means is much too big. Now the variance in the empirical Bayes means is much too small from model 1. And that reflects shrinkage. They're all being shrunk quite a lot towards the overall average due to the lack of information. But the yellow line are the empirical Bayes predictions from model 2. Now they're only slightly below the true variance. So that is the best method here. And the substantial improvement reflects the high PCV there. So then we might ask, well, how correlated do we expect the predicted stratum means to be with the truth? Okay, so the truth correlated with itself is the black line at the top, a correlation of 1. That's where we want to be. Now with the observed intersection means we're this line down here. And so with only 10 kids per intersection, we've only got a correlation of 0.8. And when we shift to the empirical Bayes predictions, that is no better. And that is because the shrinkage, which is beneficial, is a common amount to all intersections because they're all of the same size. In unbalanced data, that line would be higher and would be the preferred method. But preferred to the empirical Bayes predictions from model 1 are the empirical Bayes predictions from model 2, which are much higher because, once again, of the inclusion of the additive main effects, and they typically have a high PCV around this 0.9 value. Okay, so we're just going to end up by shifting over to the analytic results for a single intersection isolation, if you like, across repeated samples of students from that intersection. So we can say, well, if we take a given intersection, and let's say its true value is minus 0.5 in the population, but of course we've only got a sample of data, what do we expect to get back? Well, across repeated samples, we would hit that truth, and so there's no bias, that's the blue line, with the observed intersection means. With the empirical Bayes means, across repeated samples, we're going to be conservative. So if the true mean is minus 0.5 relative to the overall average of 0, then we're always going to be being pulled up, and so there's an upwards bias. That's in red. Now that upwards bias is less pronounced in model 2 because we have the fixed effects in that model, and so we're now shrinking towards the additive main effects prediction, which is very strong, and so we're pretty close. We're much closer to the truth, if you like, because of that, and therefore the bias is much smaller. Then in terms of the variance of the predictions across repeated samples for a given intersection of interest, again I'm highlighting this intersection of just 10 students in each repeated sample and a true score of minus 0.5. What we see here is the variance of the observed intersection means across those repeated samples is much higher than the variance of the empirical Bayes predictions across repeated samples. Now shrinkage, which was bad for bias, is good for variance. And then and the empirical Bayes from model 2 is much closer to 0, because in every repeated sample, what we got are the additive fixed effects being the same, accounting for 90% of what's going on, and so only 10% of what's going on is being influenced, if you like, by these repeated samples. So that's the best. But so what we want to do is combine bias and variance together. There are trade-offs, there's a bias-variance trade-off, and so we use the mean squared error as a statistic for communicating that. Smaller the mean squared error, the better. So the observed intersection means, it's the horizontal blue line. We shift to empirical Bayes predictions, and for nearly all values of true values of the intersection means, and the empirical Bayes from model 1 is going to be outperforming that. But then if we shift to the empirical Bayes prediction from model 2, that's always dominating empirical Bayes prediction from model 1. So to conclude, MAIHDA is an appealing exploratory approach for studying intersectional mean differences and individual outcomes, addresses many of the shortcomings of regression of interactions. In terms of our analytic results, those model 2 predicted means are clearly preferred to those of model 1, with both sets preferred to the observed means. Clearly, the analytic results I've shown you will vary by VPC, PCV, and degree of imbalance, but that's for a longer talk. Thank you very much. That's the end of the talk. Oh, and finally, we have a tutorial that we've written, Claire Evans and myself and others, for those who might be interested in applying this technique for their own data. That's a nice, very recent paper to turn to.